Section 5.3, roots of polynomial equations. So the following will probably be one of the most important of the techniques that we shall be using for finding roots of polynomials. So, root theorem. Let P be a polynomial with integer coefficients. Let the degree of the polynomial be greater than 0. So let this be a non-constant polynomial. Let the greatest common factor of P and Q equal 1. So that P and Q will be relatively prime for some values P. Oh, then I should let the polynomial be named F. Otherwise, how are you going to distinguish between my P's and Q's? Okay, so let me call my polynomial F. Okay, so let F be a polynomial with integer coefficients. Suppose that it's non-constant. Let P and Q be two integers. And of course, you don't want to divide by 0. And let them be relatively prime. If P over Q is a root of your polynomial, then must divide your leading order coefficient, and Q must divide your constant coefficient. So this gives us a restriction to say what our rational roots must look like. They must look like these factors of only these two numbers. So I just have to look at two numbers, find what their factors are. Then I know that the only possible rational roots must be of this form. It must be a factor of the leading coefficient divided by a factor of the constant coefficient. So let's do examples to show you how to use this technique. So first, let's just figure out what are the P's and Q's. Page 528, use the rational root theorem to list all possible rational roots of the polynomial equation. And so I have here problem number 8, 3x to the 4 minus x to the 3rd plus 7x squared minus 5x minus 8 equals 0. I want to list all the possible rational roots to this equation. So, you know, if you didn't have the rational root theorem, you'd have to try an infinite number of choices. I'm going to restrict it down to a much smaller choice, possible choices here for rational roots. So first, let's figure out the possible values of P. So what are the possible values of P? So I want to find the coefficients of the factors of 8. And so the factors of 8 are 1, and I'll do it as plus or minus. So plus or minus 1, 2, 4, and 8. Let me just see if I wrote this correctly. Okay, so that's leading. So those are factors. So Q is factors of AN. Okay. Sorry about this. In the theorem, I guess I wrote it. Did I write it wrong in the theorem? But what I've written is the roots is correct. Okay, so let's do this. So now, let's find the possible values of Q. And so Q, factors of 3 are 1 and 3. So now, let's find the possible rational roots. Of our equation. So the possible rational roots of our equation are just going to be P over Q. So let's first divide each of these by 1, the value of Q here. So 1, and I'll write it this way. 2, 4, and 8. I'm going to divide each of those by 1. Next, let's divide each of these by 3. 1, 2, 4, and 8. So this is a list of all possible rational roots. These are the only roots that could possibly of this equation that are rational. And so these are the only possibilities for rational roots of your polynomial. And so I've restricted down to an infinite number to a much smaller number of possibilities. We'll eventually figure out another way to even make this list smaller as you're going through it. Okay, so let's do problem number 10, which is to do the same thing, to find all the possible rational roots of my polynomial. Now, I usually just write down P. And so let's write all the possible values of P. And then Q. And so the possible values of Q, so the factors of 6. 1, 2, 3, and 6. And so lastly, let's write P over Q. And so let's divide each of these P's, 1 and 3, by Q, a possible value of Q. First, let's divide by 1. So 1, 3 over 1. Let's divide by 2. 1 over 2, 3 over 2. Now, let's divide by 3. 1 over 3, but then I get 3 over 3. But I've already done 3 over 3. That's here, if I reduced it. So I'm done. I don't list it. Remember that I wanted the P's and Q's were relatively prime. Lastly, let's do 1 over 6. And then 2 over 6, but again, 2 over 6 is just 1 over 3. 3 over 6 is just 1 over 2. So I don't need to list it. And so these are my possible rational roots. And I'm done. So for right now, all I'm doing is just listing them out to show you how to list out the possible rational roots. Now let's see how to use that. So now, find all rational roots of each equation. So I have an equation here. I want to see if I can find the rational roots of this equation. Once I've done that, that may be able to be sufficient to find all the roots of my equation. So first, let's find the rational roots. And so P, 1, 2, 3, 6, 9, and 18. So these are the factors of 18. Q. Oh, that's just a 1, so 1. So let's write P over Q. And so plus or minus 1, 2, 3. I'm just dividing by 1, 6, 9, and 18. These are the only possible rational roots. Okay. So the technique that I'm going to use, so I'm just going to look at this list, pick something out of the list, see if it works, and I will check to see how if it works using the factor theorem, just saying that, well, if it's a root, saying that they're using the remainder theorem first before I use the factor. Using the remainder theorem, that by using syntactic division, this will be a root so long as the remainder is 0 after I divide. So I don't know, let's try 2. I have here 1 x cubed minus 2x squared minus 9x plus 18. The reason I think that 2 will work, because I look at the symmetry here. I look at the 1 and the minus 2 and the minus 9 and the 18. This is just not negative 9 times this. So therefore, if I just solve x minus 2 equals 0, I should probably get a solution, x equaling 2. So let's see if it works. So drop down the 1 times 2 is 2. Plus 2 is 0. Times 2 is 0. Minus 9 is minus 9. Times 2 is minus 18. Plus 18 is 0. Good. So now let's try to solve this. Let's multiply, let's say 3. Okay. So drop down the 1. Oh, let's do this. Let's make it so I have enough room. P over Q. Let's just pull that up a little bit. Okay. Don't have enough room to finish this problem. Okay, so the drop down to 1 times 3 is 3, plus 0 is 3, times 3 is 9, minus 9 is 0. And lastly, let's do, well, I have enough room, minus 3. Okay. Just pull it up one more. Okay, so drop down to 1 times minus 3 is minus 3, plus 3 is 0. And so I just get down to nothing. And so this says that the rational are 2, 3, and minus 3. I actually have 3 roots to a cubic, so this is actually every root to my polynomial. So I've actually solved this polynomial. I found every rational root to this polynomial, all three of them. I found every root to this polynomial. Let me do another problem.
Professor, I have a question. How come you didn't try the other numbers in there?
Pardon?
How come you didn't put the other numbers in there? Like you only put two.
I could, in other words, some work, some don't work, right? I certainly doubt 18 would work, right? That's a gigantic number. The first number that I picked here was 2, and it worked. And then you can see I'm solving x squared equals 9. So what do you think the solutions of that are? Well, 3 and minus 3. So I could easily pick the 3 and minus 3 because I was able to solve that in my head.
Oh,
that was a right. So once I picked the 2, the other equation, so the reduced equation here is just x squared minus 9 equals 0. So that was really easy to solve in my head. So actually, I didn't even look in this list. I just plugged them in because I knew that they would work. But I'm actually picking them, quote unquote, from the list. Okay.
Now, Professor, I have a question.
Sure.
For that, regarding his question, I had the same question as well, but what happens if we don't get a remainder of 0? Do we need to still investigate? I mean, do we still have to?
Yes.
Okay.
Matter of fact, in about 5 minutes, I'll show you that getting that, don't think that you've, missed up all your possibilities. It actually helps you. Even going the incorrect route helps you to eliminate all the other rational roots. So you try something, see if it works. If it doesn't, it still helps you. So it's not like any of your time is wasted, even if you don't get that it's 0. And I will be showing that in about 5 or 10 minutes.
Okay, well, I have another question. If we get a question similar to this, does that mean you want us to solve for every number, or
Yes,
do you want
it
to
will
just...
be. You will find every root. So we will give you techniques where you will be able to, for the problems that I give you, you'll be able to find the roots. Okay. So we'll give you problems. We'll give you techniques where you'll be able to solve it. Okay.
Okay, thank you.
And then I'll tell you when you can't actually solve it. Okay, so now let's do problem number 29. X to the 4 minus 10x cubed plus 35x squared minus 50x plus 24 equals 0. So this looks kind of complicated, but that's fine. Let's see if we can do this. So first, let's find all possible rational roots. And so let's find the values of p. And so let's factor 24. 1, 2, 3, good grief, 4. Those are all factors. And then after that gives you a 6. So then now we start going down 6, 8, 12, and then 24. So those are all the factors of 24. Oh, for Q, well, that's easy. There aren't a lot of factors, just 1. So P over Q, just divide everything by 1. Well, that's just going to give you back P. Okay, come on. Okay, so now 1x to the 4 minus 10 plus 35 minus 50 plus 24. So you have here 1, 2, 3, 4, 5, 6, 7, 8, 16 numbers to choose. First number to choose, I always try, if it, right now, I can tell that one number works. And I'll tell you how to figure that out. Add up all these numbers. 1 plus 24 is 25, plus 35 is 60. Add up, and then minus 10 minus 50 is minus 60. If you add, so I know 1 works. So my guess is to try 1 first. And so if you just add up all the coefficients and they add up to 0, I know 1 works. Minus 1 will work if you switch the odd ones to change the signs and they add up to 0, you know negative 1 works. But 1, I believe 1 works here, and let's try that. Once you've figured out one of these, your life usually becomes much easier. So the trick is to find the first one. Somehow look and see which one do I think works. So let's drop down to 1 times 1 is 1, minus 10 is minus 9, times 1 is minus 9, plus 35 is 26, times 1 is 26, minus 50 is minus 24, times 1 is minus 24, which gives you 0. Okay, good. Now let's try another one. This looks like 2 works. Do I know 2 works? No. Am I guessing? Yes. I think 2 works. Let's see if it works. Because it looks like it's kind of big, but not too big. Let's see if this works. 1 times 2 is minus 7. Times 2 is minus 14. Yeah, it works. 26 minus 14 is 12. Times 2 is 24. Minus 24 is 0. And I can see which other ones work, because this is a quadratic. X squared minus 7x plus 12 is 0. So 3 and 4 work. 3. So 1. 7 is a minus 4 times 3 is minus 12, gives you 0. And then lastly 4, which I guess I have to move this up just a little bit. I'm going to have to, so I can fit this all in, I'll just move up 1 more. And so this is equal to 1 times 4 is 4, minus 4 is 0. Okay, so I get, quite nicely, the solution is 1, 2, 3, 4. So 1, 2, 3, and 4 work. So those are the roots of my polynomial thing at the end. And so I found all 4 roots of my polynomial, and they all turned out to be actually natural numbers that worked for this polynomial. Let me do problem number 36. Ooh. And so let's try 36. So P is factors of 3. 1, 3. Q, factors of 12. A lot of factors of 12. So 1, 2, 3, and then keep going down. 4, 6, and 12. So those are the factors of 12. So let's find the possible rational roots. So P over Q, these are going to be fractions. So a lot of fractions on this one. So P over Q is equal to 1 divide by 1, so 3 over 1, divide by 2, 1 over 2, 3 over 2, divide by 3, 1 over 3. 3 over 3, well, that reduces, so I don't have to do that. Divide everything by 4, 1 over 4, 3 over 4, divide everything by 6, 1 over 6, 3 over 6, well, I don't need that one, that reduces. And then 1 over 12, 3 over 12 reduces, so I don't need that one. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So 18 numbers to look at. So let's do 12. 20 minus 41. 20 minus 3. So I have a bunch of fractions. Let's try a half first. Let's try 1/2. See if that works. Why a half? The 3s and the 6s, it seems like 3s and 6s quickly will, and the 12 will not give me something that divides out nicely after it will give me a fraction relatively quickly. So I don't think I'll try those first. The 3 could work, but it may have problems with this towards the beginning. So I think a half or negative half should work. So that's my guess, is trying a half. Let's do 12 times a half is 6. Okay, 26. So times a half is 13, which gives me 28 or 38. That's 30, 41. Okay, this gives me a negative 28. This gives me a negative 14. This gives me a 6. This gives me a 3. This gives me a 0. Good. Okay, so now, once I've done that, this number here, all these coefficients here are divisible by 2. So actually, I should divide each of these numbers here by 2 now. So if I do that, I'll get 6, 13, minus 14, and 3. Okay, good. So that's just a 3 and a 6. Okay, so that means that these have to be divisible by 6. So I can get rid of a lot of choices here. So that means get rid of any of the ones here, the 1/4 and the 3/4 and the 1/12. Those can all go. So I can reduce the possibilities here. Let's try, let's try something big. Let's try negative 3. See if that works. Let's just try that. 6 minus 18 minus 5, 15, 1, and that'll give me a minus 3, 0. Okay, good. I'm going to have to go into the next page, no matter what. Okay. So now, notice I have 6x squared minus 5x plus 1, so that's a 2 and a 3. Oh no, it's a 6 and a 1. So let's try that's a 2 and a 3. Let's try a half again. And so let's try a half again. And so drop down to 6. Actually, let me rewrite this. 6 minus 15 and 1. Let me rewrite this. So I can only have plus or minus 1, a half, a third, and 1/6. That's all that's left to look at. So let's try 1/2.
Professor, why'd you
No, I've
put
tried it
negative
before, but the 2 and 3 seems to work. Yeah.
Why
Ooh, ooh, ooh.
negative 15?
Because it's a typo.
Oh, sorry.
That's what I was just erasing. I was like, what? Because also I was saying, I was checking it. I'm like, wait, that doesn't work. So if I look at this, 6x squared minus 5x plus 1, that factors into 2x minus 1 and 3x minus 1. So it should be a half and a third should work. So let's try that. So drop down to 6 times a half is 3. Minus 5 is minus 2 times a half is minus 1. So that gives you 0. So that's good. And let's try 1/3. I could reduce it, but let's just write 1/3. That becomes 6 times a third is 2, which gives you 0. Okay, so now let's find all the roots. So the roots were, one of them is a double root. The half is a double root. It's a half minus 3, a half, and 1/3. So those are the 4 roots to my polynomial. And just notice, this was I could have written it this way as 1/2 minus 3 and 1/3. And just sort of noted double root. So, or you could have listed the half twice. Either way is correct. Okay, so reduction of possible rational roots. So what I've done is I've sort of guessed, and each of my guesses I was very lucky to, when I guessed, I actually picked a root. But the question is, well, what happens if you're not so lucky and you don't get that it comes out to 0? What do you do? Do you, throw up your hands and say, well, I can't do this? No, you actually use that information to actually eliminate many of the possibilities of your possible rational roots. So it will be a much easier problem to deal with. And so sort of either getting it right or getting it wrong will help you tremendously. So it turns out that both getting the right answer and the wrong answer help, and just about help in just as much of a quantity as, in both instances. It will really help you a lot, both a correct and a wrong answer. So first, so reduction of possible rational roots. Let f be a polynomial with integer coefficients. So in all the examples I've given you so far, these are polynomials with integer coefficients. There are no fractions in the original polynomial. Suppose that f of a is not 0, meaning suppose that you pick a number where it doesn't work, where the number that you've plugged in is not a root of your polynomial. If it's a root, you're happy. If it's not a root, then use this. So suppose f of a is not 0, and suppose that a is is an integer. So you plugged in an integer value, not one of the fractions, because we don't like fractions yet. And suppose that the greatest common factor of P and Q are integer values. And of course, you don't want to divide by 0, where they're relatively prime. So you've gotten rid of all the common factors. Then P over Q is a root of your polynomial, implies that P minus A times Q must divide f of A. So it turns out that your possible rational roots are now restricted greatly by this further condition, that this sort of error that you obtained, that you tried something and it didn't work, will now eliminate from that list of possible rational roots all of the rational roots that do not satisfy this. And so from that list of rational roots, you check to see which ones satisfy this conditions, which ones don't. The ones that don't satisfy this are eliminated. So you'll now be using this error that you tried something and didn't work. That will make this gigantic list of possible rational roots. So you have this huge list here of possible rational list all rational roots of the polynomial. And let's try to solve this. In that process, I want to reduce the possible number of the number of possible rational roots to at least less than 3 possibilities. Okay, so let's do this problem. So first, let's try the rational root theorem. So let's look at P and Q. So P in this case, the factors of 10, 1, 2, 5, and 10. Q, the factors of 6, 1, 2, 3, and 6. And so let's find all the, so let's look at P over Q. Here it will be important for me to write it as over 1, 2 over 1, 5 over 1, 10 over 1. Now let's divide everything by 2. So if I divide by 2, I get 1 over 2. 2 over 2 I don't need to write. 5 over 2. The 10 over 2 again, I can reduce that, so don't write it. 1 over 3. 2 over 3. 5 over 3. The 10 over 3. Okay. And 10 over 3, okay. Divide everything here by 6, 1 over 6. And, well, 2 over 6, I don't need to write, 5 over 6. So last 5 over 6. Okay, so now let's try to solve this. So let's do, so the polynomial is -6, -1, 1, and 10. I don't have a good idea what a root of this will look like. Let's try 1. So I'm just going to guess 1, because 1 is actually the easiest number to pick. Let's pick 1. And so let's see if it works. Drop down. So I get a -6 times 1 is -6, minus 1 is -7, times 1 is -7, plus 1 is -6, times 1 is -6, plus 10 is 4. And now you go, well, it's 4. But that actually makes your life, so if it worked, you're happy. If it doesn't work, you're still happy. Okay, so now what this means is I can reduce, so use this to reduce the possible number of rational roots. The number of possible rational roots. So this was my f of a is 4. So recall that it said that p minus aq must divide f of a. So in this case, this says that p minus q must divide f of a, which is 4. So let's look at, well, let me do this naively at the beginning. So what this says is that I want to look at, well, I've already done 1. So I don't have to look at, so I have to look at these numbers. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these numbers, 24 actually of these numbers I have to look at, but actually only 23 because I've already looked at 1. So I don't have to look at 1, but let's look at 1 over negative 1, okay? And so this says that p minus q, so this is p here, 1, and q is minus 1. So 1 minus a negative 1 must divide 4. So 1 plus 1 is 2. Does 2 divide 4? Yeah. Yes, it does. Okay. Next. Oops. I hit the wrong thing. Okay. Okay, so now I've looked at, so this one isn't eliminated. Let's look at, oh shoot, 2 over 1. So 2 over 1. So again, that's p minus q is just 2 minus 1, which is 1. Does 1 divide 4? Yes. Look at 2 over negative 1, which is, well, the same as 2 minus negative 1, 2 plus 1. Does that divide 4? No, that's incorrect. 3 is not a factor of, is 3 a factor of 4? No, so that's wrong. So this means that I can eliminate the negative 2 out of this possibility. Okay. Now I could keep going with this, but, so I'll just say dot, dot, dot. But let me do it sort of nicer notation. Let me write this as what I'm doing, which is p minus q. And maybe I'll copy all these numbers here. So I'm going to do it for all these numbers. Okay. I'll just sort of write them up here. Okay. Stop that. Paste. Okay. Let's look at these numbers. Okay. So let's just look at p minus q. So I don't have to do the plus 1 because we already did that. Okay, so let's just do 1 minus a negative 1. It's 2. Okay, and then the 2 minus 1 was 1, then 3. Oh, and then 5 minus 1 is 4. 5 plus 1 is 6. 10 minus 1 is 9. 10 plus 1 is 11. So I'm sort of, notice I'm putting these commas underneath the other I'm doing, and I'm doing the plus first. So 1 minus 2, well, let's do a 2 minus 1 is 1. 1 plus 2 is 3. Doesn't work. 5 minus 2 is 3. 5 plus 2 is 7. 3 minus 1 is 2. 1 plus 3 is 4. 3 minus 1 is 3 minus 2 is 1. 2 plus 3 is 5. 5 minus 3 is 2. 5 plus 3 is 8. 10 minus 3 is 7. 10 plus 3 is 13. 6 minus 1 is 5. 1 plus 6 is 7. Lastly, 6 minus 5 is 1. 5 plus 6 is 11. Okay, so those are. Okay, so notice I can get rid of, I want these to be factors of 4. So 3, 6, 9, 11, 3, 3, 7, 5, 8, 7, 13, 5, 7, 11. None of those are factors of 4. Okay, and so that means that I've eliminated my possibilities for P over Q. Okay, so I just have, well, let's read them off. I have a negative 1. That works. I have a positive 2. That works. Oh, I've got a positive 5. I have here, that's above a half. So that's a positive 1/2 works. And then the 1/3, oh, all the thirds. So plus or minus 1/3 works. The plus 2/3 work. And the plus 5/6 works. So I've gone down to 1, 2, 3, 4, 5, 6, 7, 8. 8 numbers. So now I just have 8 numbers to look at, 8 possibilities. So I've reduced that list quite a bit, okay? Just by that one sort of error, it actually made my life even better, okay? So now let's check something else. So let's do another one. So let's try, I'm doing this sort of systematic. I'm just trying the first one on the list. Let's try negative 1. Negative 1 is also a nice one. So if I picked 1, now let's check at, let's try negative 1 and see if negative 1 works, right? And see, let's see what happens. Okay. So let's see. So I'm going to try negative 1. See if that works. Okay, so my polynomial was negative 6, negative 1, 1, and 10. Okay. So now let's do negative 6. times -1 is 6. Minus 1 is 5. Times 1, -1 is -5, which is a -4. Plus 1 times -1 is a +4. This gives you 14. Okay, so I have 14. Okay, so now I'm going to look at, so I only have a much smaller list to look at. I just have to look at this list here. Of that, so I can now use this to reduce the number of possible rational roots. So I just have to look at this. Now, of course, I don't have to look at the -1 because I've already done that. So I'm just going to look at these guys. Red looks better. So I look at P minus -1 times Q. Well, minus and minus make that a plus. So I just want to look at P plus Q. 2 plus 1, 3, 6, 3. Oh, and that's going to give you 2 of these. So 4 and 3 minus 1 is 2, 5, and 11. Okay, of those, you want to eliminate anything that's not a factor of 14. Well, that's almost everything. 3, 6, 3, 4 is not a factor. 2 is a factor. 5 and 11. So the only thing is, and that was a -1/3. So the only possibility, so this says that my rational roots, the only things I have to check now is -1/3. So I've reduced the number of possible rational roots to just 1. And actually, this one doesn't work. So actually, this particular polynomial I gave you has no rational roots. But notice I've all of a sudden made this list go to 1 number. So I started out with a gigantic number. How many did I start out with? 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 24 numbers. So I've gone from 24 numbers to just 1 number, just by doing, quote unquote, 2 errors. So those errors that you're afraid of, don't be afraid of. Use it. So use this error that you've made to actually help you to eliminate all these possibilities so that your problem becomes much more tractable. So an error is not an error. It's something that will help you. Okay, so let's try this. So this is a very big problem. So let's see if we can do this problem, which is list all rational roots of this polynomial. 60 x to the 4 minus 92 x to the 3rd minus 41 x squared plus 58x plus 24, and reduce the number of possible rational roots to a list of less than 10 possible rational roots. Okay, so we want to make this much more tractable. You don't want to check 1,000 numbers or something, whatever this will come out to be. You want it to be much, much smaller. Okay, so let's figure out what P is. So P factors of 24. So let's find the factors of 24. 1, 2, 3, 4, 6. Finally, I'm going down. Okay, 4, 6, 8, 12, 24. Okay, so those are the factors of 24. Let's find the factors. 60. Ooh, 60 is infamous for having lots of factors. 60 is 1, 2, 3, 4, 5, 6. So the first 6 numbers are factors, but then after that, it's going to go down. So next, it's going to be 10, 12, 15, 20, 30, 60. Okay, so now let's get a page. Okay, good, new page. So let's list all the possible rational roots. So let's do P over Q. And there'll be a few of them. Okay, so I want to divide each of those by 1. 1, 2, 3, 4, 6, 8, 12, 24. Okay, divide every number by 2. 1 by 2. 2 I don't have to. 3. Okay. 4, 6, 8, 12, 24 I don't have to. Okay. Now divide by 3. 1/3. 2/3. 3/3 I don't need. 4/3. 6/3 I don't need. 8/3. 12/3 and 24/3 don't need. 4. 1/4. 2/4 don't need. 3/4. 6/4, 8/4, 12/4, 24/4 don't need those. Do over 5. Oh, need everything for 5, I think. Yeah. So 1/5, 2/5, 3/5, 4/5, 6/5. Okay. 6/5. Thank you. 8/5. 12/5. 24/5. Okay, 5. So now 6. 1/6. Not 2, 3, 4, 6, 8. No, none of those others. So only 1/6. Now let's do 10. Plus or minus 1/10. 2/10, that's a header. 3/10. 4, 6, 8, 12, 24. Those all So let's do 1 over 12. 2, 3, 4, 6, 8, 12, and 24. Those each has factors common with 12. Let's do 1 over 15. 2 over 15. Don't need 3 over 15, 4 over 15. 6 over 15 has a factor. 8 over 15. 12 over 15 and 24 over 15 have a factor. So now let's do 20 plus or minus 1 over 20. Okay. Okay, so it's 1 over 20 plus or minus. So now 20. 2 over 20, no. 3 over 20. 4 over 20, no. So 4, 6, 8, 12, and 24. Don't need those. Let's do 30. 1 over 30. 2, 3, 4, 6, 8, 12, and 24 have factors with 30. Into 1 over 60. 2, 3, 4, 6, 8, 12, and 24 have factors in common with 60. So that's just 1 over 60. And then that's it. Okay, so this is big. So how many numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. 72 numbers. So there's 72 possibilities. Less than infinity, but still a large number. So we started out with an infinite number. We've now restricted it down to 72 numbers. Hopefully, I can get it down to less than that. So first, let's try 1. Okay, so for 1, my polynomial was 60, 92, 41, 58, 24. Okay, so now let's do this. So 60 minus 32 minus 32 minus C3. Okay. So 1 times minus 32 is minus 32. So you get a minus 73, which is 15. Which is 9. Okay. So I have from the above that P minus Q, because it's P minus 1 times Q, must divide 9. So P minus Q must be a factor of 9. So let's look at P minus Q. A lot of numbers here. Okay, so let's look at these. Actually, let me just copy, and I'll have to put some spaces. Copy this. So let's look at P minus Q. Okay. I have to put these as guides. Okay. Get rid. So I'm looking at P minus Q. Okay, let's list these all. P minus Q, 2, 2 minus 1, 1, 3, 2, 4, 4 minus 1, 3, 4 plus 1, 5, 6 minus 1, 5, 6 minus a negative 1, 7, 8 minus 1, 7, 8 minus a negative 1, 9, 11, 13, 23, 1, 3, 1, 5. Okay, then let's look at these guys. Okay, let's make those red so I know it's not what I want. So this is equal to 3 minus 1, so that's 2, 4, 1, 5, 1, 7, 5, 11, 3, 5, 1, 7, 4, 6, 3, 7, 2, 8, 1, 9. That's a 1, 11. And lastly, that's going to be okay. Look at these guys. A lot of numbers. Let's look at these guys, but at least a lot of them will be eliminated. Okay, so those will be 5, so 7, 17, 19, 29, 5, 7, 9, 11. A lot of these are gone, except for that 9. 7, 13, 11, 13, 14, 16, 13, 17, 11, 19. That's 8. So 7, 23, 19, and 21. And then these last ones. Okay, let's do another. Okay, so I guess I'll just have those in red and let's do it below it. Okay, so that'd be a 17, 23, 29, and a 31, a 59, and a 61. Okay, come back to me anytime, thank you. A 59 and a 61. Okay, so I want these to be divisible, be a factor of 9. A lot of things are gone. So factors of 9. Of 9. almost everything is not a factor of 9 in this list. So all these are gone. All these are gone. Okay, so all these are gone. Okay, so all those are gone. Okay, so P over Q. So what is this list now? Okay, so that's the plus or minus 2. Plus or minus 2. That's still in there. So plus or minus 2 is in there. And then the 4 is still in there. Just the plus 4. Okay, so plus or minus 2, 4, oh, the 8, that's a negative 8. The negative 8 is still in there. 8 is still in there. So negative 8. That's got to be the plus or minus a half. And then the plus 3 halves. Plus or minus a half and plus or minus 3 halves. Those are still there. Okay, next line. What's still left? Oh, the 2/3 and the 4/3. 2/3, 4/3. 2/3 and 4/3. The ones that are only one away from each other. Okay, 2/3, 4/3. The 4/5 and the 6/5. 4/5, 6/5. 4/5, 6/5, 8/5. Those are the 5s are there, strangely. Yeah. And then, do I see anything else? I think that's it. I think everything else is gone in that list. Okay, so I've reduced this down. Just with that one error, I'm down to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, I'm basically, just with that one error, I've gone from 72 to, what is it? I said 11 or something. Okay. So now it's much, much smaller. So that list is much, oh, wait, did I? Yeah, that was just the one. Okay, so, oh, the minus 1. I forgot about the minus 1. Did I not put in the, oh, the minus 1 didn't work. Oh, okay. So minus 1 didn't work actually. Okay, so then I did get rid of that. So let's just plus or minus 2. Okay. So I'm basically done. I think, what is it said? I wanted to reduce it down to how many numbers? 11 to 8 numbers. So I can still, oh, to 10. So I'm just 1 over. 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, so I'm slightly over. Okay, so I could just do this again. Say I want to look at this value at 2. I could probably reduce it down a bit. Okay, so let's do that. Oh, this is a big number. 60, 92, 41, 58, and 24. Okay, so let's do that. And so I have 60, 120, 28, 56, 15, 30, 88, 176, 200. Okay. And so I want, in this case, P minus 2Q to be a factor of 200. Okay, so I'll probably eliminate a few numbers there, just looking at that one. So let's do copy these. I'm just sort of listing these here because it's easier to figure out what all these numbers are. Okay, rather than looking above. So I have here P minus 2Q. And I already picked the 2, so it's only a minus. So I'm only looking at these guys. Even there, it's 10 numbers, or no, it's 11 numbers still, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11 numbers. Well, I'll get less than that. Okay, so this is going to be 2 plus 2 is 4. So it's, I can put the minus at the bottom. So it's 2 minus 2 times negative 1. 4 minus 2. 8 plus 2. Oh, and then there's 2 of those to look at. And so 2 minus, oh. Here, wait 1 second. Oh, I can put the minus there. Okay, so I've done that correctly. Okay, so 1 plus 4 is 5. And then 1 minus 4. There's no way to do that yet. It's 1 minus 4 is a negative 3. And then negative 1. And then 2 minus 6 is negative 4. 4 minus 6, negative 2. 4 minus 10, minus 10. 8 minus 10. Okay, so want to be a factor of 4. Yes, question.
Yeah, for the fraction negative 8 over 1, how did you get 10? I got negative 6. I don't know if I'm doing my math right.
Did I do this correct? Let me see if I did it correct. Actually, it should be negative 8 minus 2 is a negative 10. Oh, I see, or positive 10. So I could have done it. That's the way I did it, actually. Not that it really matters.
Wait, I'm getting confused. And how did you get 10?
Yeah. So I do 8 is P. Q is negative 1. So -2 times -1 is a +2. 8 plus 2 is 10. Remember, my q is a -1 here. So p is
Wait,
8.
can you go over it again?
Sure. P is 8.
Okay, P is 8.
Q is -1. So 8 minus 2 times -1. The -2 times negative was a +2. So 8 plus 2 is 10.
Ah, okay, I see.
Now, you could have gotten a -8, a -10. It's either one is correct. It just depends on where you put the minus sign. Put in the numerator or denominator.
Okay.
Okay?
Thank you.
So in this case, it didn't matter. Okay, so factors of 200 actually doesn't eliminate that much. It only gets rid of just gets rid of the 3 and the 6. That's it. Only gets rid of 2 things. This one didn't help a whole heck of a lot, but at least it got me. And so in this case, at least I eliminated enough that I'm under how many I wanted to look at. So in this case, the P over Q. Again, this was just a problem so that you'll see how to do it. But so P over Q, -2, 4, the -8 still works. -8 worked. The +1/2 worked. The 3/2 worked. 2/3 worked. 4/3 worked. 4/5 did not. 6/5 worked. And 8/5 worked. So this was more work than it helped actually in this case, but at least it got me to 1, 2, 3, 4, 5, 6, 7, 8, 9. Got me to under 10 numbers. And so those are your possible rational roots. So I've at least gotten from that gigantic list of 72 numbers to 10 numbers or 9 numbers. Okay? So this was meant to be a practice on a difficult problem to eliminate, from such a large number of possibilities, to at least give something that's semi-manageable. Okay. Unfortunately, probably then you'd have to start doing fractions because this is not really, now it's not helping as much to be eliminated. Okay, so let me give you some examples on non-existence. So what if, so you shouldn't be trying to find rational roots if you know that there are no rational roots. So let me give you a non-existence theorem. So the non-existence of rational roots. Suppose you have some polynomial with integer coefficients and the constant coefficient, the leading order coefficient, and the value of your polynomial at 1 are all odd numbers. Then you know that your polynomial has no rational roots. So this is a fairly easy criteria to look at. You just look at 3 numbers. Okay. So let's look at the following polynomial. F of x equaling 5x to the 6th plus 2x to the 5th minus 6x to the 3rd plus x minus 5. And I want to show that this polynomial is irreducible over the rationals. Okay. So, did I say this? Yeah, it has no rational roots. Okay. So, first thing to note is that the constant term is odd. Next, note that the leading order coefficient is, well, a sub 6 is also odd. So notice that the first and last, we're just looking at the first and last terms. The first term and the last term are odd. Then lastly, check the value of your polynomial, which can be at 1, which can be found by just adding up all the coefficients. So what I really do is I just say, and this is usually the way I do it. Let's call it F1. I just take the coefficients and add them up. So 5 plus 2 minus 6 plus 1 minus 5. That's the way to determine the value of my, and so let's see what this is equal to. Well, 7 plus 1 is 8, minus 11 is negative 3. And this is an odd number. These three numbers are odd. Therefore, by the above theorem, I have that this polynomial is irreducible, meaning it has no, so this is irreducible over the rationals. So I can't factor this over the rationals. Okay, so that's an important thing to note. Okay. Let's look at the following.
Can this be a method for the previous examples? Can this be
Okay,
like
you'll have, I'm sorry, you'll have
a
to,
way to check every question?
yeah, you'll have to repeat what you said because you faded out.
Oh, I'm sorry. I said the question that we just did right now, can that be a method to check for the previous questions?
Oh, if it was applicable.
Previous questions to be further
Right. So I have to give you some more theoretical things. Yeah. Okay. So what you notice is that in this particular problem, yeah, in this particular problem, in this particular problem, your
yes.
the leading order coefficient term are not odd. So I know that this would not be, that the theorem I gave you would not be applicable. So it would not have helped us in that case. Okay, I hope that's what you were asking. You broke up quite a bit during the conversation, but I hope I'm answering what I think you asked. So in the previous problem, we could not have used this just because there were it's not applicable. The leading order coefficients were and the constant term were even. Okay. So let's try to see. Let's determine if the following is irrational. Okay, so let's determine if the following has rational roots. And so I have x cubed minus 2x squared minus 3x plus 19 equals 0. So let's first see, is this irreducible? So that's the first step. And so notice that the constant term is odd. The is odd. And I don't know, let's call this f of 1 or something. And the sum of the coefficients is 15. Which is also odd. So therefore, I know that this polynomial is irreducible. So I have that this is an irreducible cubic. Okay. But since this is irreducible, so this is irreducible cubic over the rationals. So this is irreducible over the rationals. And it's a cubic equation. And since it's a cubic equation, well, the only way that a cubic equation can factor is if it is a polynomial of degree 1 times a polynomial of degree 2, or 3 polynomials of degree 1. But however it factors is it would have had to have a polynomial of degree 1 in it, in the factoring of it. Therefore, if it is irreducible, it means that it has no factor of degree 1. Therefore, it means it has no roots. And so for a polynomial degree, this means that irreducibility, in this case, means that there is no rational roots. There are no roots of this equation. And so irrationality says that there are no rational roots. And so in this case, we found that this polynomial has no rational roots because it's a polynomial that's of a low degree. Okay, let's do some further criteria. So I'm going to give you a whole bunch of additional criteria that you can use to help you in several situations. Not in every situation, but at least in several. Cohn's irreducibility criterion. Suppose that B is some natural number not equal to 1. And suppose that I have a polynomial with integer coefficients. And suppose I have that P at this number B is a prime number, and that every coefficient in my polynomial was between 0 and this number B. Then the polynomial is irreducible over the integers. Okay, so let's do an example. Nope, that wasn't that. Okay, so let's do an example. So I want to show.
Can you repeat the rule again, please?
Repeat this.
Yeah.
Which one? Yeah. So I have that. Suppose I have a number B that is a natural number not equal to 1. And suppose I have a polynomial that has only integer coefficients. Actually, there'll be whole number new coefficients, where the polynomial evaluated at this number, b, is a prime number, and every coefficient in the polynomial is between 0 and less than that number b that I found. Then the polynomial is irreducible over the integers. Okay, so we want to use, well, I'm going to give you an example here to show you how to use this. So, oh, and maybe I'll do this. Okay, so I want to show that f of x equaling x cubed plus 5x squared plus 3x plus 6 is irreducible over the integers. So let's look at, so basically I want to figure out, can I evaluate this at some point? And it has to be a number. So first, the criteria is that all these coefficients are between 0 and some number, and they are. They're all greater than or equal to 0. And I want to pick some number that's bigger than all of these coefficients. So pick a number bigger than these coefficients, such that when you plug in that number, you get something that's a prime number. Okay, well, let's do that. I doubt if 6 will work, so let's try 7. So that's 1x cubed, 5x squared, 3x plus 4. So let's pick that. So it's 1, 7, 12, 84, 87, 609, 613. Okay, so 613 is a prime number. You can just check by looking at the your divisibility numbers. And so it's not divisible by 2, 3, 5, 7, 11, 13, 17, or 19. So it's irreducible. And so it's a prime number. So 613 is prime. Every number, every coefficient satisfy. Oh, well, maybe I'll have to do it in this weird notation that they're between, right, the coefficients 1, 5, 3, and 4, and they're all less than 7. So meaning there's 4 inequalities there, and all the coefficients are integer valued. Then by Cohn's irreducibility criteria, we have that f is reducible. Over the integers. And that's and so you've shown that it's irreducible. Okay. Let me do another example. Same sort of thing. I want to show that this is irreducible over the integers. And so I have here Well, maybe I should show that. So I have 2x cubed. So let me actually show that. Okay, so I have 2x cubed, 2x cubed plus 5x squared. Let's just clear all this. Okay, 2x cubed plus 5x squared plus 3x plus 5. Okay, let me check this. My table settings. Start 0, no, ask. Okay, it's a little slow. Good. Okay. So now let's set up a table. Why did it not work there? Okay. Okay, quit. Table. Good. Okay, so let's plug in something. So I want a number bigger than 5. So let's try 6. So 6, 7, 8. Okay, so that's 12, 21. So 6 and 7 are not prime. 8 is prime. So let's pick 8. Okay, so let's do 8. So let's just pick 8 and see what happens. So 2, 5, 3. So 2, 16, 21, 168, 171, 1368, 1373. Okay, so 1373 is prime. And all the coefficients, 2, 5, 3, and 5, those are all less than 8. And so Cohn's irreducibility criteria says that this polynomial is irreducible over the integers. And that's what you wanted to show.
What's the reason you chose 8 again?
Because I looked and I had to pick something bigger than 5. So if I noticed 6, see the 635, that's divisible by 5. I looked at 7, 957, that's divisible by 3. But 8 is 1373, so that's a prime number. I wanted to find a prime number. So I wanted to find some number bigger than 5, some integer, a whole number greater than 5, so that when I plug into the polynomial, the output is a prime number.
Oh, okay, thank you.
So that's why I use the calculator, sort of to cheat, to see which one I should try. So the one I should try is 8, because 8 worked.
Would we have to show that we tried the other numbers before? Or...
No.
Okay.
Oh, you can just say I tried 8. Okay. Next, Eisenstein. So Eisenstein's irreducibility criterion. So this is another irreducibility criteria. Let f of x be a polynomial with integer coefficients. And suppose that constant polynomial, so the degree of the polynomial is equal to n, which is greater than 0. And suppose that p is some prime number. So you're going to pick some prime number p such that the following holds. P does not divide the leading order coefficient, but it does divide, that divides everything else. But p squared does not divide the constant term. Then f is irreducible over the integers. So you find some prime number which divides every coefficient except for the leading order coefficient, and such that p squared does not divide, then it's irreducible. So if you can find some prime that does that, then you know it's irreducible over the rationals. A prime ideal. P is a prime ideal if A times B, being in P, implies that A is in P or B is in P, where P is some subring of some commutative ring R. So Eisenstein's irreducibility criterion in general says, let I be an integral domain, let P be a prime ideal in I, if F is a polynomial with coefficients in this prime ideal, where the coefficients of F are relatively prime, with A sub n not being in the prime ideal and A sub 0 not being in the square of this prime ideal, then F is irreducible over I. So let's do some examples. Show that 3x to the 6th minus 7x to the 5th plus 49x to the 4 minus 28x to the 3rd plus 14x to the 2nd plus 21x minus 35 is irreducible over the integer, over the rational numbers. So first, I want to find some common prime. So what's in common here? Well, it's pretty obvious. There's only really, besides 1, there's only one number that's in common with all these numbers, 7. And so let's try 7. So if I look here, 7 is in common. So 7 is a prime number. So that's good. That's one of the requirements for Eisenstein. Next, I have that 7 is a factor of minus 7. It's a factor of 49. It's a factor of negative 28, of 14. 7 divides 21. And 7 divides minus 35. Okay. Okay, good. So those were the criteria. Next, I want that 7 squared. 49 does not divide negative 35. Well, certainly 49 is not a factor of 35. So all of the, well, and of course, each of the coefficients here are integer valued. Then by Eisenstein, I have that this polynomial is irreducible over the integers. And so it was fairly obvious you would just pick 7 here. Okay. Let's look at the next one. Show the following polynomial is irreducible over the integers. So f of x equaling x to the 4th minus 8x cubed plus 14x squared plus 8x minus 14. Well, the only prime common factor between these, actually the only common factor besides 1 is, I guess, 2, a common factor. And so let's see if it works. So choose prime. Okay, so that's a good thing. 2 does not divide 1. 2 does divide 8, 14. It does divide at 8, and it does divide negative 14. So that's good. Next, 2 squared, 4, does not divide 14. All the coefficients are integer valued. So by Eisenstein, I have that this polynomial is irreducible. Okay, good.
On a test, will you tell us which one to use?
You'll just say, it'll say factor this or show that it's irreducible, and you'll have to know which criteria. You could use several different criteria to show that it's irreducible. It'll say show that this is irreducible over the integers or something.
So we
Okay.
can choose one.
So you'll have to see, can I use this criteria to Eisenstein or Cohn's or the oddness sort of thing to show this irreducible. So you'll that's it. Okay.
Okay.
Okay. Next, finite fields.
Wait, Professor, can you repeat that again? It kind of faded away from me.
Oh, I'm sorry. Okay. So he was asking if I would specifically say which criteria to use to show if things are irreducible and on the test. So all we will say on the test is that to show that some particular polynomial is irreducible, let's say over the rationals. And so you'll have to choose which of these to see which of these either oddness or Cohn's or Eisenstein, which of these you can use to show that it's irreducible. Sometimes you can use more than one of these. Other times, maybe only one of these criteria will work. Okay. Okay, so now a finite field. So a finite field, f sub p, is a field with p to the n elements where p is a prime number. So the modulo irreducibility criterion. If f is irreducible over f sub p for some prime p, and this is the leading order coefficient of f is not 0 mod p, then f is irreducible over q. So irreducibility over some finite field shows irreducibility over the rational numbers. So let's do an example. Show that the following polynomial is irreducible over the integers. And so let's do this. Well, let's just look at Z2. So on Z2, well, f of x, all I'm going to do is look at the evenness and oddness of this. And so this is just 1x cubed. This is 1x squared. This is no x's because it's an even number. Plus, this is an odd number, so that's plus 1. Okay. You can add by any multiple of 2. And so I subtracted 14 from this one, added 74, subtracted 842, added 1288 to get this. Okay, so now let's look at this. So let's check to see if this is irreducible. Okay, so now I'm going to show that x cubed plus x squared plus 1 is irreducible over Z2. So I'm going to show that. Well, first off, since this is a cubic, then, as I said before, to show irreducibility over a cubic, well, one of the factors has to be linear. Therefore, I just have to look at a root. And so, let's see if I can find a root of this polynomial. Well, first off, well, f of 0 is 1, which is not 0. So therefore, 0 is not a root. Let's look at f of 1. Well, 1 plus 1 plus 1 is again 1. So that's not a root. So I'm just going to check everything. So f of 1, this is an odd number, so it's just 1. Okay. So there are no. So I've checked only 2 possibilities. For Z2 just involves 0 and 1. I've checked neither of those are roots. And so neither zero nor 1 is a root of f of x. Therefore, f of x has no roots. In Z2. One second. There are the roots in Z2. Now, since f is a cubic, then f must have if f factors f of x must have a linear factor. But we've shown that f cannot have a linear factor because there are no roots. But then this would imply that f has a root in Z2, and it does not. So therefore, f of x is irreducible over Z2. Over Z2. Which implies f of x is irreducible over Z, over Q. By the modulo irreducibility criteria. Okay. So this was really, if you looked at this, this was really something involving, you could have used the fact that the oddness thing. So from the beginning. So we could also use the fact that A0, AN, and F sub 1 are odd to show that F is irreducible over Q. So in reality, this ability that I gave you for the oddness was really the same as irreducibility modulo 2. So these tests are really quote unquote the same. Oh, okay, so note the following. If I looked at x squared plus 4x plus 14, notice that that does not factor over the integers. You can't find two whole numbers whose product is 14 and whose sum is 4. So obviously we know that we can't factor this. But if I look at Z2, then this reduces down to x squared. And of course, x squared factors is x times x. But the irreducibility says that if it's irreducible, then over, say, ZP, then it's irreducible over Q. It doesn't say if it factors over ZP, then it factors over Q. So the fact that it factors doesn't tell us anything. So the theorem does not hold, does not apply, because it only tells you when it's over ZP, then it's irreducible over Q. Okay, so let me do an example of factoring over, let's say, Z5. So let's do an example of that. So let's look at what happens on Z5. So Z5 consists of, we can think of it as consisting of 0, 1, 2, 3, and 4. So I can always add a multiple of 5 to make it look simpler. So this is x cubed. Let's add 5 to the negative 4. to make it x squared. Let's, and then plus 3x. Let's add 5 to the negative 5 to make that 0. Okay, so I can factor this as x times x squared plus x plus 3. Okay. So let's try to factor this. Notice 1 plus 1 plus 3 is 5. So that means that that's a root. So let's try to actually factor. And let's do it this way. So I have 1x squared plus 1x plus 3. Drop down the 1. Times 1 is 1, plus 1 is 2. Times 1 is 2. Plus 3 is 5, but mod 5 is 0. Okay. So this says, let's add. So this says f of x is equal to x times the x squared plus x plus 3, which we said was, well, x minus 1 times this, which is x plus 2. Again, we're doing the z5. So let's call this, let's add 5 to this. So x, negative 1 plus 5 is 4 times x plus 2. And so I have factored, this is on z5. I have factored my polynomial on z5. So x cubed minus 4x squared plus 3x minus 5 factors into x times x plus 4 times x plus 2. And that is your answer on z5. Okay. Gauss's lemma. Okay, so Gauss's lemma says irreducibility over the integers implies irreducibility over the rational numbers. So sometimes I may have said that accidentally. So if f is a polynomial with integer coefficients, and if f is irreducible over the integers, then f is irreducible over the rational numbers. And so notice what that means. That if f has integer coefficients, then factoring over the integers, if you're able to factor over the integers, then you're able to factor, I'm sorry, let's say it over again. I said it wrong. If you're able to factor over the rational numbers, then you're able to factor over the integers. You can just multiply by the least common denominator to get rid of here. So if you're able to factor with rational coefficients, then multiplying out by the least common denominator means that you can factor over the integers. Okay, so show that p of x, only 2x cubed plus 5x squared plus 3x plus 5 is irreducible over the integers. Well, we showed that like 5 minutes ago, that this was irreducible and so by Gauss's lemma, I know that this is irreducible over the rational numbers. Okay. Oh, okay. So in general, if p of x is some polynomial, then the greatest common factor of p means the greatest common factor of the coefficients of p. So Gauss's lemma says let U be a unique factorization domain and F be its field of fractions. Then P being a polynomial with coefficients in this field of fractions. And the greatest common factor of P being 1, meaning that all the coefficients are relatively prime. Then P is irreducible in U if and only if P is irreducible. Okay, lastly, this is about the last of that I'm giving you. Irreducibility invariant under translations. So let F and G be polynomials, a non-constant. Then there exists, and suppose there exists a number such that f of x is equal to g of x plus a. Then f being irreducible over f is the same as g being irreducible over f. So the fact that you've done a translation doesn't change this irreducibility. So let's do this one. I want to show that x to the 7 minus 7x to the 6 plus 21x to the 5th minus 35x to the 4th plus 35x to the 3rd minus 21x squared plus 55x minus 73 is irreducible over the integers. Okay, so if you notice, this is like a 7 and all that. So these look like you can get rid of these by just adding 1. So I should be able to get rid of this guy and maybe at least make these easier, especially these guys, by just looking at what happens at 1. So let's look at f of x plus 1. So if I do that, this is x plus 1 to the 7 minus 7 x plus 1 to the 6 plus 21 x plus 1 to the 5th minus 35 x plus 1 to the 4th 35 x plus 1 cubed. So a lot of these will cancel. Oops. Minus 21 x plus 1 squared plus 55x minus 73. So this is equal to x plus 1 to the 7th is x to the 7 plus 7 x to the 6, 21 x to the 5th, 35 x to the 4, 35 x to the 3, 21 x squared plus 7x plus 1 minus 7 So that'll be x to the 6 plus 6. X to the 5th plus 35. No, wait. $14. One, 6, 15. 15, sorry, 15, 20. How did I mess that up? Plus 15. Sorry, plus 15, x to the 4. Plus 20, x cubed. Plus 15, x squared. Plus 6x plus 1. Plus 21, x to the 5 plus 4, x to the plus 5, I messed up, plus 5, x to the 4, plus 10, x cubed plus 10, x squared plus 5x plus 1. Okay, that's a 21. Minus 35, x4, four x3, that'd be what, a 6? X squared plus 4x plus 1. That's 4 plus 35. X cubed plus 3x squared plus 3x plus 1. Minus 21. X squared plus 2x plus 1. That's 21 plus 55 x minus 73. Okay, so this is equal to x to the 7 plus, those all cancel. So x to the 6's cancel. X to the 5th, so that's 42 minus 42. These cancel. Okay. Now x to the 4th. Let's look. So I'm looking basically going this way. Okay, so these canceled. Now let's look at these guys. So 35, that canceled with that. So the 4th canceled with this one. And then you get 105 minus 105. Those can't, the fourths also cancel. So those cancel. Now let's look at the cubes. Okay, let's look at the cubes, see what those guys. I got a 35 and a 35, that's 70. And I have 70, oh, so that's a 70 and a 280 minus 140 is 140 minus 140. These all cancel. These all cancel. Okay, so those all can't, a lot of things cancel. So far everything is canceled. Let's look at x squared. 21 cancels with that 21. 210 and 105. And that is a 70, a 105. Okay, so this cancels. So 7. Oops. So these cancel. Okay, so those cancel. Lastly, let's look at the x's. See if these guys cancel too. Okay, so I have 7. Oh, well, let's not do that. That's 105. And that's a 4 times that. It's 120, 140. So 140. Okay. That's a 42. And there's that's a 42. That's a 42. Okay. That's a 84. So that's 84. And a 55. Those don't seem to cancel yet. So those don't cancel quite, but almost do. A lot of things cancel. So 7 minus 42. So I guess I'll just have to do it out. So 7 minus 42 plus 105 minus 140 plus 105 minus 42 plus 55. So adding all these up, you get a negative 7 plus 55 gives you 48. Oops, x. So you get a 48x. So a lot of things canceled. And then looking at the constants, you get 1 minus 7 plus 21 minus 35 plus 35. Obviously, those canceled. Minus 21. Oh, actually, I should cancel those guys. So let's cancel out these guys. The 35s and the 21s. I'll cancel out those. So all you have left is negative 73 minus 6. So that's a negative 79. Oh, plus the 55. I forgot about that 55. Okay, so sorry about that. Okay, so I have a 1 minus 7 plus 55 minus 73. So I get a negative 24 after I add up everything. So a lot of things canceled actually. So I just have to look at this guy. Let's see if I can do Eisenstein on this guy. 2 wouldn't quite work. Obviously 2 is a prime and it divides both 48 and 24, but 2 squared is 4, so that would be a factor of 24. So let's try 3. 3 is a prime number. Try 3, so 3 is prime. So this is going to be much easier because there's not a lot of things to check with this guy. So 3 is prime, and I have that 3 does not divide 1. 3 does divide 48. 3 does divide negative 24. But 3 squared is 9, which does not divide 24. So therefore, by Eisenstein, I have that this polynomial, I think I called it f, is irreducible over the integers. I forget if I did Eisenstein as integers or rationals. It's irreducible over Q. Again, it doesn't matter by Cauchy's lemma. If I would have said integers over Q. Okay, so Viete's formulas. So let me quickly sort of say about Viete's formulas. So we'll derive some formulas under some special cases first. So first, the quadratic. So assume that x squared is equal to minus ax minus a sub 0x plus a sub 1. And suppose I can factor it as x minus r1 times x minus r2. So suppose somehow I can factor it. Let's try to figure out some sort of conditions on these roots r1 and r2 involving these a0s and a1s. Well, if I multiply this out, I just get x squared minus r1x minus r2x. Factor out the minus x. So I get a minus r1 plus r2x. Minus r1 times minus r2 is plus r1, r2. So I get that r1 plus r2 is equal to a0. r1 times r2 is a sub 1. These these are symmetric polynomials in R1 and R2. Notice that interchanging R1 with R2 does not change these polynomials. So I have these two polynomials in R1 and R2. If I just said, well, instead of calling this R1, I'll call this R2, and I'll call this one R1, well, it still satisfies the same equations. And so interchanging R1 and R2 change these symmetric polynomials. These polynomials here are called elementary symmetric polynomials in the two variables R1 and R2. Every symmetric polynomial of degree 2 in the variables R1 and R2 can be written uniquely as a polynomial of degree 2 in these two elementary symmetric polynomials. We call R1 plus R2 the first power sum. We call R1 squared plus R2 squared the second power sum. Both of these power sums are symmetric polynomials. Note the following. R1 plus R2 squared is R1 squared plus 2R1, R2 plus R2 squared. That's just the special product formula. Let me write R1 and R2 squared together. So this is R1 squared plus R2 squared plus 2 R1 times R2. R1 plus R2 is just A sub 0. So A sub 0 squared is equal to R sub 1 squared plus R sub 2 squared plus 2. Well, remember R1 plus R2 is A1. And so R1 squared plus R2 squared is A sub 0 squared minus 2 A sub 1. And let's just look at the cube. R1 plus R2 cubed is R1 cubed plus 3 R1 squared R2 plus 3 R1 R2 squared plus R3 squared. R2 cubed. I said it the wrong way. Let's write the R1 cubed and the R2 cubed together. So R1 cubed plus R2 cubed. Let's group these and let's factor out R3 R1 R2 times what remains, which is R1 plus R2. R1 plus R2 is A0. R1 plus R2 is A0. R1 times R2 is A1. So R1 cubed plus R2 cubed is A0 cubed minus 3 A0 A1. So let's summarize what we've written here. The power sum relations. R1 plus R2 is A0. 2 squared is A0 squared minus 2A1. R1 cubed plus R2 cubed is A0 cubed minus 3A0A1. You can do the same thing for cubics. Suppose I write my polynomial as x cubed minus A0 x squared plus A1x plus minus A2. And suppose I want to factor it as x minus R1 times x minus R2 times x minus R3. Let's find a relation in R1, R2s, and R3s. So if I multiply this out, I get that this is equal to x cubed minus R1 plus R2 plus R3 x squared plus R1 R3 plus R2 R3 plus R1 R2 x minus R1 times R2 times R3. So we get R1 plus R2 plus R3 must equal A0. R1 R3 plus R2 R3 plus R1 R2 must equal A1. And R1 R2 A3 must equal A2. Again, these are symmetric polynomials in R1, R2, and R3. Elementary symmetric polynomials, actually. Just like before, you could do R1 plus R2 plus R3 squared, which is just R1 squared plus R2 squared plus R3 squared plus 2. R1, R2, R3. Well, R1 plus R2 plus R3 is just A0 squared equals the sum of R1 squared plus R2 squared plus R3 squared plus 2 times, well, again, this is A sub 1. So you get R1 squared plus R2 squared plus R3 squared is A sub 0 squared minus 2 A sub 1. So R sub 1 plus R sub 2 plus R sub 3 cubed, you could regroup, is R sub 1 cubed plus R sub 2 cubed plus R sub 3 cubed plus 3 times the product of R sub 1 plus R sub 2 plus R sub 3 times R1, R2 plus R1, R3 plus R2 R3 minus 3 times R1 times R2 times R3. So you get a sub 0 squared, a sub 0 cubed is equal to R1 cubed plus R2 cubed plus R3 cubed plus 3. This is a sub 0 times a sub 1 minus 3 times a sub 2. So to summarize, we have R1 plus R2 plus R3 is A0. R1 squared plus R2 squared plus R3 squared is A0 squared minus 2 A sub 1. R sub 1 cubed plus R sub 2 cubed plus R sub 3 cubed is A0 cubed minus 3 A0 A1 plus 3 A sub 2. For the quartic, you could do the same thing. You could just say, well, x to the fourth minus A0 x cubed plus A sub 1 x squared minus A sub 2x plus A sub 3. Let it equal x minus R1, x minus R2, x minus R3, x minus R4. If you multiply that out and regroup, you get, again, the same relationships as before. Get a sub 0 squared is equal to the sum of the squares plus 2 a sub 1. You get that the sum of the roots cubed can be written as the sum of the cubes plus 3 times A0, A1 minus 3, A2. So, to summarize, R1 plus R2 plus R3 plus A0, R1 squared plus R2 squared plus R3 squared plus R4 squared is A0 squared minus 2A1, R3 squared plus R2 squared plus R3 squared plus R4 squared is A0 cubed minus 3A0 A1 is 3A2. So, let's summarize the summary. For linear equations, R1 is R0. Quadratic, R1 plus R2 is R0. Cubic, R1 plus R2 plus R3 is A0. Quartic, R1 plus R2 plus R3 plus R4 is A0. So notice that for any polynomial, the sum of the roots of the polynomial is A0. That's all this is saying. Next, let's look at the squares. Throw out the linear, because it's actually not. Guess you say, well, once you get a polynomial, once you get a power that's higher than the degree of your polynomial, then you have to make the other terms 0. Okay. Otherwise, the formula, it cuts off. It only gets the first part of the formula correct, then the other parts are going to be 0. Okay, so now for quadratic, cubic, and quartic, notice that the sum of the squares of their roots is always equal to a sub 0 squared minus 2a sub 1. So this is a universal sort of pattern. Next, again, let's do the cubes. Notice for the cubes, I got to get rid of things that polynomials of degree less, because it won't follow the same pattern. But the sum of the cubes will always equal a sub 0 cubed minus 3a1 a0 plus 3a sub 2. Again, so long as you get rid of the polynomials of degree less than 3. Okay. So notice that, and you'll have similar patterns. So notice that you can always write the sum, these power sums, as some relation relationship in the coefficients of your polynomial. Okay. The discriminant. The discriminant, D, is defined as the product of the difference between all the roots. So, and of course, you don't take two roots, you don't take the difference of two roots that are equal. So if I want to say this explicitly, since I'm taking, since R1 minus R2 is the same as R2 minus R1, if I want to write this so that it's written, well, in, say, decreasing order, then I'll just say it's the product of R sub j minus R sub I quantity, or 1 less than or equal to I less than j less than or equal to n. And this is for a polynomial of the form x minus R1, x minus R2, dot, 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 x minus Rn. This discriminant, so it's just any monic polynomial. This is a symmetric polynomial in the roots R1 through Rn. And so, in particular, for the quadratic equation, say p of x of the form x squared minus a0x plus a1, the discriminant has the form R2 minus R1 squared. So multiplying this out, you get R2 squared minus R1 R2 plus R1 squared. So it's R1 squared plus R2 squared minus 2 R1 R2, which from above I know that the sum of the squares is just a0 squared minus 2a1. The product of the roots is just a1. And so I get a sub 0 squared minus 4a sub 1. So if I had ax squared plus bx plus c, then the discriminant for this is just, well, b squared minus 4ac. It's something you've seen before. It's our discriminant. Okay. For the cubic, x cubed minus a sub 0 x squared plus a sub 1 minus a sub 2. My discriminant just looks like r sub 2 minus r sub 1 squared, r sub 3 minus r sub 1 squared, r sub 3 minus r sub 2 squared. Multiply this out, group everything together. So you get a sub 2 squared minus a sub 1 squared minus 4 a sub 0 cubed, a sub 2 plus 18 a0, a1, a2 minus 4 a1 cubed minus 27 a sub 2 cubed. So what you notice is that for any discriminant, even though it's written in terms of the roots, you can actually rewrite them by some algorithm to be in terms of the coefficients of your polynomial. So for a reduced cubic, a cubic of the form x cubed plus px plus q, the discriminant has the form negative 4p cubed minus 27q squared. Let me quickly finish this off. A cube root of unity. Let omega, the fancy w, equal 1/2 times the quantity negative 1 plus I rad 3. Then omega squared is, well, 1/2 squared is 1/4. Negative 1 plus I rad 3 squared. Let's square this. So by the special product formula, it's just negative 1 squared 1 minus 2 I rad 3 plus I squared, which is the negative 1, rad 3 squared, which is 3, so minus 3. 1 minus 3 is a negative 2. Factor out of 2, So you get 1/2 times -1 minus I rad 3. Notice that W squared is just the complex conjugate of W, of omega. Omega cubed, well, is just the omega squared times omega. Since they're complex conjugates, you just get 1 plus 3 is 4, which cancels with 4, so you get 1. Called a cube root of unity because the omega cubed is 1. It's the cube root of 1. So how do you solve the cubic? So this is a modern viewpoint of how you solve polynomials. So this was done by Galois in 1828. So when he was about 16. So step 0. Divide. So suppose you have some polynomial, cubic, ax cubed plus bx squared plus cx plus d equals 0. First, divide by a, so that I can assume that my polynomial is monic. Next, after you've made it monic, do a change of variables, like what we did last week, to get rid of the quadratic term. And so you can assume that the polynomial has the cubic has the form x cubed plus px plus q equaling 0. So your first step to solve this is to solve an associated quadratic polynomial. And so the first step is to actually find the hidden polynomial inside of your polynomial you want to solve that is simpler to solve than the original polynomial, and it is found, will be found by using some symmetry of your coefficient. So we obtain this equation using the following. So let omega equal 1/2 times -1 plus I rad 3, the unity. Recall that omega squared is just the complex conjugate of omega. And let mu sub 1 equal R1 plus R2 omega plus R3 omega squared. Let mu sub 2 equal R1 plus R3 omega plus R2 omega squared, where R1, R2, and R3 will be our desired solutions of x cubed plus px plus q equaling 0. And these desired solutions will be retrieved from step 3. So it's easy to show by just cubing this. So if you cube this and add them together, you'll see that mu sub 1 cubed plus mu sub 2 cubed is 27 R1, R2, R3. But I know from above that R1 times R2 times R3 is just Q. So I know that mu 1 cubed plus mu 2 cubed is 27 cubed. Similarly, mu 1 times mu 2, just multiplying it out, is a negative 3p. And so is a negative 3 R1 plus R2 plus R3, which becomes P. And so mu 1 cubed plus mu2 cubed is negative 27p cubed. And so mu1 cubed and mu2 cubed are just solutions of this quadratic equation, x squared plus 27x minus 27p cubed equaling 0. So we found this hidden equation hiding inside the cubic using, well, it's called this alternating group a sub 3. Mu sub 1 cubed and mu sub 2 cubed are fixed by a sub 3. They remain unchanged if we cyclically permute R1 going to R2, R2 going to R3, R3 going to R1. And they're interchanged if we swap any of the two R's together. Say R1 is interchanged with R2, R3 is interchanged with R3, etc. So step 2. So basically, step 1 is just to solve. So step 0 was to put it into the form x cubed plus px plus q. Step 1 is to solve x squared plus 27 qx minus 27 p cubed. So solve equaling 0. Solve that. Okay. Next, after you'll call those roots mu1 cubed and mu2 cubed. Take a cube root, any cube root of mu1 cubed, and you'll obtain mu1. Then, using the fact that we had above, let mu2 equal minus 3 p over mu2. So now you know what mu1 and mu2 are. To determine R1, R2, and R3, well, it's easy actually, to show that if I have these two equations, I can then figure out what R1 and R2 and R3 are as follows. R1 is just 1/3 mu1 plus mu2. R1 omega plus, mu2 omega plus mu1 omega squared. R3 is 1/3 mu1 omega plus mu2 omega squared. So notice that these still have that same sort of symmetry from above. Okay. So lastly, let's just do this. Uh-oh. I want to solve the following equation over the complex numbers. Solving this over the complex numbers. 9x cubed minus 45x squared minus 4x plus 20 equaling 0. Given one of the roots is the negative of the other root. So I'm going to use this relationship between the roots to actually solve to help solve the equation. So this will give you a hint at what I was just talking about. Okay, so let one root equal A. Let the other root equal minus A. Okay? And let the third root, and this is a cube root, so let the third root be B. Okay. So I have 9 x squared, x cubed, plus 45 x squared minus 4x minus 20. Suppose it's equal to, well, let's write a 9 out in front. X minus A, x plus A, times x minus B. And then let's figure out what A and B are. So this is equal to 9 x squared minus A squared times x minus B Let's multiply this out. So this is x cubed minus bx squared minus minus a squared x plus a squared b. So this is equal to 9x cubed minus 9bx squared minus 9a squared x plus 9a squared b. Okay, so I get that. Well, equating coefficients, 9 is equal to 9, so that doesn't give me anything. But negative 9b is 45. And so from here, b is negative 5. Good. Next, 9a squared. Going to give me a fraction, is equal to 4. And so that says that a squared is equal to negative 4. I'm sorry, I wrote something wrong there. Is equal to negative 4. And so I have that a squared is equal to 4 over 9. So a is equal to plus or minus 2/3. I could either pick plus or minus. It doesn't really matter. Because one is, you notice, a and negative a are solutions. So I could pick, let's say I pick a to be the positive 2/3. Then the other one will be negative 2/3. Okay, so let's, oops. So this is positive 2/3, let's say. And then lastly, I have that a squared b, that a squared b is equal to negative 20. Let's see if that works. Well, let's see, a squared is 4 over 9. And b is negative 5. Oh, and I wrote, of course, I forgot the 9 there. So 9a squared b, is this equal to negative 20? Well, these cancel. So yes, indeed, that works. Okay, so the solution to this equation is, well, plus or minus 2/3. Maybe I'll write it a little further. So plus or minus 2/3 along with negative 5. So those are my 3 solutions to my equation.